Our new mesh is ready, generated with remeshing libraries, but the real challenge is how do we integrate it into our solver? Let's break it down. Hello everyone and welcome to my channel. In the previous chapter, we selected a remeshing criterion to decide where and when the mesh needs to be updated. This could be based on distortion, element quality, or other geometric metrics. Now, to continue the solution after remeshing, we need to map the essential variables from the old mesh to the new one. On the nodal side, we map displacement, velocities, and accelerations, which are crucial for maintaining the dynamic states of the simulation. On the elemental side, we transfer fields like stress, strain, plastic strain, and other material history variables to preserve physical accuracy. My mapper used two tailored strategies. For nodal variables, it applies nodal weights, distributing contributions smoothly from nearby elements. For elemental variables, we use a more robust nearest node search. Each new element simply inherits values from the closest original node, ensuring stable and efficient remapping even with large mesh changes. Here we are seeing the results of a mesh refinement using omega h based on an angle criteria, just like in the previous video. Notice how the refinement is concentrated in the central zone, adapting to areas of high distortion. The visualization is done with ParaView, giving us a clear look at how the mesh changes in response to geometric conditions. You can see how elements are subdivided in real time, increasing the resolution where it matters most. Now we are looking at the second refinement process. This one kicks in only after the equivalent plastic strain crosses the 20% threshold. Just a few time steps later, as in the earlier example, the simulation stops unexpectedly. This could be caused by multiple issues. One possible is that the time step isn't updated dynamically. The scheme is unconditionally stable, but a large time step may still introduce inaccuracies. Another likely factor is the poor mapping of elemental fields during remeshing. Since the fields are piecewise constant, transferring them to the new mesh can introduce errors that destabilize the run. In the previous video, we introduced MMG, a remeshing tool that works quite differently from omega h. Unlike omega h, which can locally refine, MMG always performs a full remeshing process, replacing the mesh entirely rather than refining it incrementally. Here we are showing the remeshing process using MMG. The code used for this example is the file remesher mmg.c, and the main entry point is the function generateMMG. It all starts with a call to mmg initMesh, which initializes the mesh structure. Then we set the number of nodes and elements using mmg3d set mesh size. After that, we provide the actual mesh data. This means passing in the nodal coordinates with mmg3d set vertex and the element connectivity with mmg3d set tetrahedron. Now comes the part that controls the remeshing resolution. We use mmg3d set sol size to define how many solution values we will pass, and then assign the size field with mmg3d set scalar sol. In this case, unlike omega h, where you define a metric by giving the inverse of square of the target size, MMG takes the actual desired element size directly. Finally, the remeshing happens with a single call to mmg3d, mmg3d-lib. The mesh is updated in place, and that's it. You've got a fully remeshed domain. Here, opening the remeshed result in ParaView after deforming a cylinder under compression. On the right side of the screen, you can see the new mesh. It's clear that this isn't just a local refinement, it's a completely new mesh. MMG has remeshed the domain based on the element size field, resulting in a significantly different configuration compared to the original. Now we are looking at a case where remeshing is triggered later, after several deformation steps. The result is similar, a full remeshing, but this time we also see a distorted mesh indicating divergence in the explicit solver after remeshing. This happens because we didn't update the minimum time step after remeshing. When remeshing, there are four main ways to map boundary conditions. First, node-based nearest search, which finds closest node in the new mesh. Second, projection onto surface triangles, where all nodes are projected into the new surface geometry. Third, interpolation via closest surface, using barycentric coordinates for smoother mapping. And fourth, exact geometric mapping, which uses the CAD or analytic surface to transfer boundary data precisely. In my implementation, I use the mapBC function inside right domain, which maps boundary conditions by looking for the nearest node in the new mesh. While simple and fast, this can introduce some errors, especially if the surface was altered or significantly remeshed. Stay tuned, we will dive into more advanced mapping methods in the next videos. If you're into FEM, SPH, CFD, remeshing, or just enjoy watching solids get squished by clever math, you're in the right place. I dive into open source solvers, GPU acceleration, and how these methods actually work under the hood. So hit subscribe, or better, hop on the mailing list at opensourcemech.com. No spam, just good stuff. And if you want to support or ask deeper questions, there's always my Patreon. Thanks for watching and happy coding!